the organizers for the opportunity to participate in this momentous occasion. When I first started learning about the basics of Chabauty-Kim theory almost 15 years ago, I was amazed to see all of my favorite ingredients being mixed together in what seemed like a witch's brew. And producing these incredibly concrete results by seeming magic. So I started learning and made a bit of progress on the problem that was suggested by Stefan Wevers while I was a postdoc in Hanover. And then in 2012, that doesn't gonna work. I went to this workshop in Bel Airs in Barbados, which I think might not have been mentioned so far. And Min-Hyang was giving this series of talks in the mornings.
Looks
like shed that you see here. Sorry?
Yes, looks like with.
As you can see, the shed has no, I mean, the shed means it has no walls. It was a really charmingly exotic setting. Lectures were held in the morning and in the evening because in the middle of the day, it was too hot to attempt to run a brain, I'm sure. So Min-Hyang spoke in the mornings, and then in the evenings, other people spoke. I believe this might be, are there any guesses? I think that's Henri Darmon. Anyway, I attempted to, I contacted all sorts of people and got lots of actually help from Henri contacting people to find photos. And the closest thing we could find to Min-Hyang actually lecturing is this photo that came ultimately from Eyal Goren. Anyway, I mean, this shed is also, just to give us a sense for the setting, it's the water is like 50 meters that way. I remember all of this as if it was yesterday. And their lectures were interrupted by occasional downpours. And there were some additional participants that you can't quite see here. They're sitting like further over there, and they were monkeys. Anyway, so
Just the same here. There are beaches over there.
Well, it's not a bit more than 50 meters. Temperature is different. Anyway, Min-Hyang gave this incredible series of lectures. Anybody who's seen Min-Hyang lecture knows how incredible they were. After the lectures, Chabauty-Kim theory no longer felt like a witch's brew. It felt like a theory that had the weight of necessity behind it. And over the years since then, Chabauty-Kim theory has remained front and center in all of my work. It's fair to say that I'm Chabauty-Kim theory obsessed. Of course, also, I mean, other people have said this, and I do. I find Min-Hyang also very, very inspiring on a personal level. I think if I go into too much detail in that direction, I'll feel embarrassed. But in any case, I want to say that maybe turning 661 might not be a momentous occasion, but this conference is a momentous occasion because it gives me a rare opportunity to attempt to the impossible, which is to thank Min-Hyang for a gift of really great proportions. My life just wouldn't be the same without it. Okay, so having finished the important part, we go on to the mathematical part of the talk. We'll be talking about work in progress together with David Borwen. Work in progress means that there should be an article in the archive sometime soon, but we hope that the main results are still beyond that article in the future. There's also a closely related article by David Borwen, by the way, which has been in the archive for several years already. And so just in kind of a quick outline for those who are some of the background. There's this long story of using the methods of mixed state motives to approach Chabauty-Kim theory to make the sort of potentially computable things more computable. And that means, but mixed state motives means that we're largely restricted to like P1 minus 3 points. And so then there's this ongoing project of ours to try to extend some of the mixed state methods beyond the mixed state setting, natural frontier, and in some ways a particularly interesting frontier I find is the setting of mixed elliptic motives. I didn't want to start by spending 45 minutes on reviewing the mixed state theory, so I'll try to sort of do both at once. But so then let's and actually the main results will take place largely in a kind of axiomatic setting, in fact, so far. So but I don't want to just start listing axioms. So let's put ourselves in this concrete setting. So consider E, so Z first of all, an open subscheme of spec Z, E an elliptic scheme over Z. We'll assume, for reasons that I'll mention later, that E does not have CM, and X the complement of the origin. Then Grothendieck's theory of the alpha suggests one way of thinking about the integral points, right? The integral points here are integral points, I mean morphisms of this, sections of this morphism from X to Z. Minhyung's approach suggests a kind of variation on that. Of course, we've already had several talks about the basics of Chabauty-Kim theory, and so you know that by now the Chabauty-Kim theory can sort of be approached from two opposite directions. And in fact, Kiran did a beautiful job of kind of like giving Chabauty-Kim theory a hug from all directions. Here I want to emphasize just this one of the two sides, and maybe I can just add to what has already been said, just these vague diagrams, these vague pictures. So so if you were working with like the section conjecture, then you imagine maybe X being spread out over B, and then picking a geometric point, like spec of an algebraic closure of Q, and looking at the fiber of that. Of course, this doesn't look that much like an elliptic curve, and I don't think that this looks I really doubt that Z looks like that, right? We increasingly prefer to think of Z as being three-dimensional. It's just a very, very simplified diagram, obviously. And but anyway, but then one way to think of the change is that then you replace finite et al. So yeah, so sorry, in the previous slide, I don't remember, maybe I didn't say this in the previous slide, you play some game with finite et al. Coverings everywhere. Like for example, if you have a finite et al. Covering of X, and you have a section, and you can pull it back. And instead you can have motives here on Z, and I guess that also means working with motives on X. And then, in some sense, that means that instead of fixing an algebraic closure of Q, you fix a fiber functor, like a realization functor, like de Rham realization. And then you can work with the vector bundles with integrable connection on X. That sort of somehow a bit parallel to looking at the geometric fiber in some sense. Of course, we don't have a category of motives in some sense. We have its derived category, but not the category itself. But we do have systems of realizations, so that's one possible fix. Another possible approach, which is the more popular one, is to work with p-adic Galois representations satisfying various Selmer conditions. And since my main results are somewhat formal, they're a bit agnostic with respect to this choice. I don't want to overemphasize right now systems of realizations, though I think they sort of connect more with the direction that we're particularly interested in. So I want to have them available. I'll just say something brief about them. They're complicated, unfortunately, so giving a complete definition. But just to give an idea, there are many realizations of H lower 1 of E. So what do we mean by that? For example, you can take H1 of the topological space of the associated complex analytic space, and that then has a sludge structure in it. You can take p-adic et al. Homology of E base change to Q bar, and that has a Galois action for an EL. You can look at the p-adic de Rham cohomology, and then and base change E also to then to QP, I guess, and then you get what's called a filtered phi module. So the filtration comes from just sort of like a stupid filtration on the de Rham complex, while the phi module structure, the phi, refers to the action of Frobenius coming from the crystalline cohomology of the special fiber. And here maybe I should have said that we should look at prime that's in Z, so a prime good reduction. And these are related by various comparison isomorphisms. Some bolt together all of this data in some way to get category of such things. I'll denote by MM cis of Z. MM stands for So this is like the Tanakian category of mixed motivic systems of realizations over Z with Q coefficients. So for those who are maybe familiar with, say, some of the versions, there are various versions available in the literature, and one that I'm particularly familiar with goes back to Deline's book about P1 minus 3 points. But we update that's you can update that in a few ways, and let me just mention two of them. Remember both of them. So one of them is that in view of work of Olson and Vologodsky and others, now we can add p-adic Hodge theoretic comparison morphisms in here without losing the unipotent fundamental group. Another one is that Deline is really kind of wants to restrict attention to those systems of realizations that actually come from the category of motive, the conjectural Tanakian category of mixed motives. But at the time he wasn't able to make that precise. But in view of the work of Levine, Hanemura, Vovadsky, and others, Ayub, Sisinski, Tiglis, we actually have the triangulated category of motives, and you can use that then to say which systems of realizations should be considered motivic. So we get a little closer to the category that ultimately we work. And now, actually, we want to adapt to the particular variety we're interested in. And again, I want most of the talk to keep in mind in the background this the case of mixed elliptic things. So let M sub E cis of Z be the Tanakian category generated by H lower 1 of E and closed under extensions. And we fix E, the point of, say, a Z point of X for use as base points. There's also a business of tangential base points that I might secretly use, but don't wish to spend much time on. And then,
So is it X E minus the identity? Is that it?
yeah, X is the complement of the origin in E. Yeah, that's right. Yeah. Okay, and then unipotent fundamental group is a pro-unipotent group object of this category. And I added this tilde because I'll actually want to spend more time with a choice of a finite type quotient, a finite dimensional quotient. We've already seen this happen in other talks. So what is this this thing? So yeah, so I mean, I guess a system of realization consists of Betty data, de Rham data, p-adic et al. Data, and then their realizations mean that, I guess this just means that we restrict attention to some of those. So what does it mean that you, the pro-unipotent group somehow with those kinds of data. So in particular, there's a Betty realization, and that doubles as the pro-unipotent completion of the topological fundamental group of the associated complex analytic space. That can be worded differently. It can also be worded as the Tanakian fundamental group, the category of unipotent local systems on the associated topological space. That description motivates the description of the realization. So U tilde of XB de Rham, the Tanakian fundamental group of the category of unipotent vector bundles with an integrable connection on XQ. Now, fix a prime in our arithmetic base Z, and then you can also talk about the filtered phi realization. So this means the de Rham realization base change to QP. Fundamental group, it's also, you can think about it again as a fundamental group of the category of unipotent vector bundles with integrable connection on XQP, but now equipped with some extra structures. So for example, there's a Hodge filtration and a Frobenius automorphism, just as there would be for the cohomology of reduction over QP. And all of this can be generalized if you fix we have our one fixed base point B, and now if you fix another point, then there's also a torsor object. So it's a torsor under a metal group and has these various realizations available. And now, so we've already seen some. Yeah, so we've already had Coleman integration show up in a few talks. I'd like to actually sort of open up the foundations of Coleman integration a bit as developed by Amnon Besser, partly as a way of actually motivating our main results. So the p-adic Durham realization of the path torsor they had above C is equally defined, right? If I just want this filtered phi realization, p-adic realization, then the base points can just be ZP points. And I said we have a Hodge filtration. So in particular, there's a sub space of this torsor, which will denote F0 for Hodge filtered degree 0, which forms a torsor under L 0 of the unipotent filtered phi realization of the unipotent fundamental group. And we'll refer to these as the geometric Hodge paths. For given 2 points, we have some special kinds of paths between them, the geometric Hodge paths. Additionally, given 2 points, we also have a special path that's fixed by Frobenius, unique Frobenius fixed path. So this is a theorem due to Besser, to Amnon Besser, and to Vadim Balagotsky, definitely. So now, okay, let's call these the geometric crystalline paths. So between any 2 points, we have a family of special Hodge paths and one especially special crystalline path. Now, well, we can use them to construct loops, right? So now if I have, and that gives rise to a map that'll denote by alpha, and that's what's called the unipotent p-adic Albanese map. So, okay, so given, so what is it? So given a point x of x over zp, I can take the crystalline path in one direction from the base point B to x, and then take the Hodge path going back. That way I get a loop, the Nakian loop. So in other words, a point of this u, v, x, f, e thing. Now there was the choice of a geometric Hodge path that I had to make the arbitrary choice. So the result is only well-defined modulo fill 0. And so you get this map like this. And so this would be called, I guess, the unipotent Albanese variety associated to this quotient of the unipotent fundamental group of X. And this, I guess I would call the unipotent Albanese, p-adic unipotent Albanese map. And let me mention, discuss the connection with I already mentioned the Coleman integration. Let me just briefly discuss the connection. So there's this sort of old story that Dick already mentioned in his talk, affecting functions on the unipotent fundamental group with iterated integrals. So given any element of the tensor algebra on H upper 1 the Ram of E, you can construct a associated function on the unipotent de Ram fundamental group, f sub omega. Now, if f omega happens to factor modulo the degree 0 piece of the Hodge filtration, then you can compose f omega with alpha, right? So alpha goes from x of zp to the unipotent variety, and then function to get to a1. And so then this composite is given by p-adic integration. Okay, and that's sort of a bit somewhat close to being a methodology. It's not so far from the definition of these integrals. There's a bit of non-trivial work to connect to Besser's definition really with this thing. but really exactly the same ingredients go into the good definitions they've given here and the definition of these integrals and in Besser's formulation. Okay, so having talked about these geometric Hodge path and geometric crystalline paths, I'll switch now to sort of the arithmetic setting and explain that we've discovered that or would like to suggest that there is a reasonable arithmetic analog of those things in some way. So first of all, we have this category of mixed elliptic systems, mixed elliptic systems of realization over in subscheme of spec Z. Right? And I can take then the Tanakian the de Rham fiber functor. So tensor automorphisms of this functor. And I couldn't choose a notation, so sometimes I'll want to emphasize Z and put Z there. Sometimes I'll want to emphasize the fiber functor and put de Rham there. Sometimes I'll have some mixture. In any case, that thing then sits in a short exact sequence like this. So I said that we take define category. I said that we H lower one of my elliptic curve E and then close up under sort of Tanakian operations and then also under extensions. But if I forget the extensions, then I get a semi-simple category, a feature of our systems of realizations that I didn't emphasize before. So its fundamental group is a reductive group. Really just, this is sort of like just a motivic. I can never remember the name of this group. Sorry, the image of okay, let me since I'm forgetting the name, I think it appears in a later slide. Anyway, I've told you what this is. Sorry, Mumford-Tate, the motivic Mumford-Tate group. Who said that? I didn't see where it came from. Oh, thank you. Martin could give this talk probably better than I could. Okay. So anyway, so we have the motivic Mumford-Tate group here in blackboard bold G, and then G of Z, the big thing, surjects onto G with Z to G with a big pro unipotent kernel. Yeah, maybe I should have said this here. We've already seen something similar to this in Dick's talk. That, for example, the abelianization of this big pro unipotent group, the product over E-reps, of a weighted product of extension group in my category of systems of realizations. And I'll use the terminology, the somewhat confusing terminology, which Martin has tried to talk me out of calling this thing the unipotent fundamental group of Z. Sometimes it's helpful, but the constructions aren't really that parallel. Sorry, just to make a quick remark, which might clarify something that comes a bit later, is I said this is non-canonically split, but why is it split anyway? It's split because there's a number of other natural fiber functors that can be taken, which will appear later, but will play a central role in the present. We can pre-compose the Rham realization with associated graded with respect to the weight filtration. And if we do that, if we make that change, then the sequence becomes canonically split. So speaking of Mumford-Tate group, under our assumption that E does not have CM, it's sort of well known that it's a blackboard bold G is just GL2. Okay, and then we had the filtered piece of the unipotent fundamental group of the fiber of X, and now there's also a filtered piece of this kind of arithmetic unipotent fundamental group. Like the fundamental group, maybe I should have written Z's here. So I would like to think of this as anyway, a filtered piece of an arithmetic fundamental group, just given by one way of defining it is just consisting of those Tanakian loop, which preserve Hodge filtrations in all objects of category systems of realizations. Now, let me abstract away from our concrete setting in order to state in a way. So, I've talked about applications which will be more concrete, but in any case, So this category of mixed elliptic systems of realizations is an example of a weight filtered Tanakian category. So what does that mean? That's just a Tanakian category, a neutral Tanakian category for us equipped with separated exhausted filtrations. Morphisms are strict with respect to the filtrations, and pure objects are semi-simple. And the RAM realization is in a natural way a what we call a Hodge filtered fiber functor. So that's just a tensor functor from our Tanakian category. By the way, you wanted in this axiomatic setting. Now I prefer to denote the Tanakian category by T. Okay, but in the applications, T will mostly be elliptic systems over Z. And now the RAM realization becomes just a tensor functor from T to the category filtered vector spaces, finite dimensional, separated, exhaustive, such that if I then forget the filtrations, I get a fiber functor. And in this, again, this axiomatic setting, let's denote the RAM realization just by the more neutral looking letter omega. And similarly,
So a comment, filtered vector spaces are not Tanakian.
true, yeah, that's right, yeah.
So then it's not really a fiber functor.
No, sorry, you're right. This fiber functor is not, I wouldn't call that a fiber functor. I'm just, but I impose the requirement that if I further, overheating the projector, I'm sorry. I further impose the requirement that if I compose tensor functor with the forgetful functor to just plain vector spaces, then I get a fiber functor. And in a similar way, crystalline realization forms a what we call a Frobenius equivariant fiber functor. So that's a tensor functor to QP vector spaces. I'm working over Z over an open subschema spec Z for simplicity. So there's no action on QP itself, rather it's the identity. And then we mapped here to vector spaces equipped with automorphism. And we require that operator phi is required to act with eigenvalues of weight n on the weighted pieces for the weight filtrations. Okay, and then the theorem A says the following thing. And so maybe somewhat sudden, though I try to make it not too sudden, appearance of these two variations of our Hodge filtered fiber functor. So on the one hand, I take the tensor functor, the Hodge filter before, and on the other hand, I pre-compose it the GER W. And then we consider tensor compatible natural transformations between these two not fiber functors, usually. But require that they induce the identity on the associated graded objects. And then the theorem says that such things form a trivial torsor under fill 0 of the arithmetic fundamental group. So maybe another way that's maybe helpful to think about this is in terms of having a path like this with that this assumption. It's the same thing as having like functorial splittings of Hodge filtrations, but those are required, which are required to also respect Hodge filtrations. And so the theorem says that there's a torsor of such things. The emphasis by far is not on the torsor, but on the fact it's not just a pseudo torsor. In other words, just on the existence. And since I won't doubt I'll get into the proof much, I should mention that, well, I mean, this takes place at the level of Tanakian generalities, but still it's not, requires some real work. And a lot of that work was done by Paul Ziegler, an article about filtered fiber functors. And so these are our arithmetic Hodge paths. And then similarly, theorem B says that there's a similar type of structure respecting infravenii. So I can take my crystalline, my Frobenius equivariant fiber functor and pre-compose it with GER W, or I can just take Frobenius fiber functor, Frobenius equivariant fiber functor itself, and then this time there exists in nice parallelism, a nice rhyme with geometric setting. There's a unique tensor compatible natural transformation that induces identity and associated graded objects. This is our arithmetic crystalline path. Okay, so now for theorem C, towards theorem C, let's fix an arithmetic Hodge-path arbitrarily in this big pseudo torsor of arithmetic Hodge-paths. So that's something that at least it was hard for me to accept, but I'm coming to accept it. And then we can define the what we call the unipotent p-adic period loop by composing these in some order. So we can take the crystalline, the Hodge path in reverse order, and then the crystalline path. And this means, I guess, that the way I've written it, this is a QP point. Maybe I should have this on the board because this really should appear. This is a QP point of this arithmetically defined the unipotent part of this arithmetically defined fundamental loop. See the ROM. That's the type of thing that this fractor U is. Hopefully familiar to those of you who are familiar with the theory of periods. I'll try to say something about that towards the end of the talk. And then there's some comment here that maybe should be longer about. But maybe I should stop for a moment before saying this and just maybe I should just say something about periods. So in the periods in the title of the talk. So in the complex analytic setting, I guess that integration defined the C-valued point of the torsor of paths from the ROM realization to Betty realization. And the Grothendieck period conjecture says that thing is maps into the generic point. In other words, the associated map of rings going the other way is injective, and elements in its image are called periods. Elements in the image of the map of rings. And there was kind of a classical theory of by now classical theory of periods of mixed state, p-adic periods of mixed state motives, in which something like this showed up in somewhat constructed in somewhat different language, by I think by Goya Mashipta and also by Chatzistemathieu Unver. I'm kind of forgetting the history of it. Okay, but so our construction is sort of an attempt to generalize their construction in a way that interfaces well with Chabauty-Kim theory, and that led us to these two paths, and that's also why it's called a period loop. Sorry, but maybe I should say one more thing. Just that I mentioned how so in the complex setting you have this spec C valued point of the torsor of paths between the ROM and Betty realization, which means that periods compare two rational structures on the cohomology. Whereas here we're not so it's not worded that way. It's more we're comparing. For example, there's nothing from p-adic Hodge theory in this picture. We're just comparing two structures available in the p-adic ROM cohomology, and the two structures are Frobenius on the one hand and Hodge filtration on the other hand. And yeah, so that's well, it could be confusing. I wanted to highlight it, and also with time permitting, I want to mention a competing construction by others at the end of my talk that is a bit more similar to the complex picture actually.
Okay, maybe I have one question. Just to make sure I'm following correctly. So this is the same as the p-adic point that appears in this description of the localization map.
Yeah, and in fact, you're predicting a theorem. Yeah, so that's our main application. So in theorem C, we'll let I guess it'll appear in a few slides. So let's let P pi now be an effective unipotent group object of T. Effective means concentrated in negative weights. Like for example, we'll apply this to the unipotent quotient of the unipotent fundamental group of our fiber X. So it's a geometric thing. And let P be a torsor object. And so, yeah, so I think the thing I skipped is that in this setting, just like in real life, torsors are equipped with a unique Frobenius fixed point, right? Our geometric crystalline paths. So let P, let's denote that thing by P super CR. Maybe note at this point that I'm using this kind of font, whatever that is, for geometric paths and fractor or arithmetic paths. And so the theorem says that if I apply our unipotent p-adic period loop to a geometric crystalline path, we get a geometric Hodge path. In other words, a path that lies in Hodge filtered. Yeah, so said differently, our unipotent p-adic period loops interchange geometric crystalline paths and geometric Hodge paths. Right, so the choice that I was unhappy to make gives us consistent choices of the geometric Hodge paths everywhere, and I'd like to make those choices. So from now on, whenever we encounter a crystalline path, we'll use it to choose a corresponding geometric Hodge path. And okay, now I'm sort of ready for the theorem that Min-Hyung wanted to see. So our main application, we're most interested in the mixed elliptic setting, but there's nothing really, I think, to prevent this theorem from occurring in the more general setting. For instance, X could be a suitable model of a hyperbolic curve with motivic Mumford-Tate group blackboard bold G. And then,
So this is no longer an punctured elliptic curve.
well, I'm most interested in the punctured elliptic curve for now, but this theorem is somewhat more general than that.
Yeah, but if you take out more than one point out of a curve, it's no longer pure. H1's no longer pure.
Oh, yeah, does that ruin?
Take out n points, you have an n-1 dimensional space in weight minus 2.
Yeah, that's true. But I'm not so sure I need that. Do I need that? Sorry, Mike, that your question is throwing me off slightly, but I think it's okay. I think it's okay. I'm not so sure I can convince you that it's okay. Maybe to be safe, I should restrict attention to the case that I'm interested in right now. Thanks for the question. Okay, so yes, we have a commutative diagram like so, and this is sort of our version of Kim's cutter, the square diagram that is shows up in all talk about Chabauty-Kim theory. So on the one hand, we have the integral points mapping into the ZP points for some chosen prime in our arithmetic base Z. And then we have here the p-adic unipotent Albanese map, which I talked about earlier, landing in the p-adic unipotent Albanese variety, which is just recall the p-adic Durham unipotent fundamental group modulo L0. And then here we kind of modified things a little bit. So sort of disassembled the H1 variety that usually defines Kim's Selmer variety into space of cocycles. So right, we take cocycles from the sort of arithmetic unipotent fundamental group to the geometric unipotent fundamental group, require our cocycles to be equivariant under blackboard bold action of blackboard bold G. Okay, and then what are these two maps? So kappa, the vertical map for like unipotent Kummer map, is just given by sending given a point, a Z point, little x of big X. Recall that we fixed a base point that's secretly in here, right? We have a base point B. Now given a second point, then we can put it to the co-cycle that sends a loop gamma in here to gamma acting on the Hodge path, the geometric Hodge path connecting the base point B to our new point X, and then its inverse. So this just means we've essentially taken, right? We take a point to a second point to the torsor as connecting the 2 points, and then but then we associate to the torsor a co-cycle, a well-known operation, but we have sort of a good choice of a co-cycle, one that's G equivariant.
So the statement, I guess this occurs in many places, but is there a unique G invariant
Yes,
cycle?
there is, yeah, that's right, yeah. Yes, I mean that, let's see, so the statement is that this is actually just the same as the H1 variety, yeah, that's right. And the H1 variety here, of course, you have the G, all of G, not just U.
It's possible that where you have to be a little bit careful about the next question.
Okay. Thanks, yeah. Okay. Okay, so then what does evaluation at sorry, what does this map do? Well, as the name implies, and as Minhyang already mentioned, it's just evaluates at U, right? We have this spec QP valued point of this group here, and then given the co-cycle, you can evaluate it and get then a QP valued point of U of X. And then we just project down to the quotient modulo.
So what was U again?
Sorry?
What was U?
U is this, well, it's the same U that I just wrote on the board
Oh, I
here,
see.
and it's this whole construction, right? So given we have these
Yeah, sure.
two ways of splitting Hodge filtrations, one compatible with, sorry, two ways of splitting weight filtrations, one compatible with Hodge filtrations, the other compatible with crystalline turbinii, and we compose them. Well, I wanted to have systems of realizations available for the discussion to follow, time permitting, but actually for one of the concrete applications, I also want to also have p-adic Galois representations available. So let me just say briefly that this story lifts to a setting of in which instead of system of realizations, you work with appropriate categories of Galois representations with good reduction over Z. And then U becomes a point of this pro-unipotent group over QP, U of Galrep. And here then we take the p-adic et al. Realization of the unipotent fundamental group, and this morphism that I had in the bottom of the square above factors through this evaluation morphism. Yeah, so we can also work with this if we wish. So a few comments about these disassembled Zellner varieties. So if we work with p-adic Galois representations, then this Z1 pointed set regarded as a functor in QP algebra, so I could take the QP algebra and base change everything, and then this thing just becomes the same as Young's Zellner variety, so in particular representable by finally applies affine scheme. On the other hand, if I do work with systems of realizations, then this thing is merely conjecturally representable. On the other hand, if we one of the things we wish to do is to sort of like, I mean, there's sort of two things you can do with these things, which I'll in the sequel. One is to try to actually maybe I should go back and remind people of the sort of basic rubric of Chabauty-Kim theory. I don't know. Yeah, so I mean, right. So what do we actually want to do with the square diagram? Well, we want to construct functions here that vanish on the image of this morphism here, and then we pull them back along alpha, and that way we get locally analytic functions on X of ZP that vanish there. And sort of two sort of types of things that we can hope to do. One is to just argue for the existence of a function of this sort living in some finite dimensional space of known functions that vanishes there. And then solve for coefficients using like the method of undetermined coefficients by plugging in points. Another sort of thing we can hope to do is to really more actually compute the image, really compute. And in the mixed state setting, we really computed. And we're also hoping to get better at computing beyond the mixed state setting. But then, yeah, so if we want to really compute, then actually the representability isn't the first problem, or it might not even be so necessary. So the representability of this is essential if you want to really just compare dimensions, because it has to be a dimension of something.
I guess the difficulty with this representability is we don't know what the use that the round is actually.
We don't know what, sorry?
The structure of this use that the round, the arithmetic view.
Yeah, that's right. Yeah. So I mean, for example, there are these X groups, and those X groups are sort of conjecturally related to K groups. But even those, I believe, are not known to be finite dimensional in any reasonable generality.
So the analog of this in P1 minus 3 points is very transparent.
Yeah. Yeah, that's true. That's true. But on the other hand, maybe I should say that at some point there should be a discussion of the pros and cons of these two options. Let me postpone it by a moment. So yeah, but maybe by just a moment. So first of all, I've already outlined the construction of what we call Kim functions. So you take this evaluation map using in the p-adic et al. World, in the world of p-adic et al. Representations, and then pull back functions on X of CP. On the other hand, we have this motivic variant using the motivic version that I use, meaning using systems of realization. So these are both collections of locally analytic functions on X of CP, which vanish on X of Z. And as I've indicated, our construction should make motivic Kim functions more computationally more accessible in various ways. And both I don't mean to say, I don't want to emphasize this distinction, but both of these have their advantages and disadvantages. There's certainly more people prefer these. I like these because of their potential relationship with periods. Anyway, the sort of thing, to just do a comment on the grave problems that Min Young, for example, just brought up a moment ago, with like not knowing the X groups, is that the sort of thing that we might nevertheless be able to hope to do with these things. It's similar to the sort of thing that in the state setting. There too, ultimately, even if we knew the size of certain X groups, these X groups which are closely related to K groups that show up. Other conjectures that we needed, but at least we had an algorithm that really spits out the set of integral points provably when it halts, but then the halting depends on deep conjectures. So that's maybe sort of the sort of thing one can hope for, even without proving deep open conjectures in using these systems of realizations. Yeah, whereas if you want to more sort of just compute dimensions and then use the method of undetermined coefficients, then we use this. That's what we'll use in the examples that I'll be giving. Okay, so I'd like to mention two examples. So I emphasized at the beginning the new frontier, or a new frontier, which is for us, which is a mixed elliptic setting. But actually, I want to like skip away for a moment and go back to mixed state motives and highlight some recent advances in that realm. So, well, Z is still an open subscheme of spec Z, namely Z a half, but now X actually will just be P1 minus 3 points. And this is joint work with David Corwin, and who's a co-author throughout these slides, and also with Martin, who is sitting over there. Already contributed something to my talk. And I just want to sort of mostly just flash in front of you a kind of concrete output that we can get. So we prove that X of ZP admits the motivic Kim function that looks like this. You'll see in a moment why this is recent and not old, but why it represents some form of progress, but let me just say a bit more about the symbols appearing here. There are these Lees of 1, for example. These are certain iterated integrals of dz over z and dz over 1 minus z. And on the other hand, there's these coefficients. So these are like p-adic iterated integrals. Yeah, and on the other hand, there are these coefficients like zeta, p-adic zeta of 3. And I want to say a bit about these two types of ingredients that show up here. First of all, to comment on the newness, so it's new here. So this function occurs in motivic weight 8, so hence beyond the quadratic quotient that received a lot of attention in the literature. Motivic weight 8 means half of means people working with mixed state motives would call this 4, I guess. And in a different direction, what's exciting to us is that it goes beyond the polylogarithmic quotient. So we're sort of used to working with the semi-simple quotient of the unipotent fundamental group setting. That means that the co-cycles that we work with are actually homomorphisms. But now there's actually a highly non-trivial action bending our co-cycles. And yet Martin basically taught us how to deal with this problem. And there should be a preprint. There should have been a preprint on the archive already quite some time ago. And in it, you will see again this function appearing in the whole algorithm.
Okay, could I ask a question about that function before? So do you find this function without using the integral points?
Yes, we do.
Oh, right, I didn't realize this. Oh, that's very impressive.
Yeah. So let me say, getting a little short on time here, but I would like to mention periods. So let me say a bit about what's special about this zeta of 3 thing, and then I can express what's missing in the next example more clearly. So the word, for example, dt over 1 minus t, dt over t, dt over t, it can be used, as I indicated before, to construct a function on the Duram. Sorry, the Duram is maybe missing here. On the Duram unipotent path torsor from 0 to 1. I'm now using this theory of tangential base points. So then you can just pre-compose, right? We have the geometric Hodge path, good choice of geometric Hodge path in here from 0 to 1. So then we can pre-compose f omega with the orbit map of the geometric Hodge paths, and then that way we get a map from a function on this arithmetic unipotent fundamental group. So MTM here refers to the category of mixed state motives over Z. Let's call that, denote that function, but by zeta f of 3, where f stands for like formal period. These things appear in the literature under various names, but were studied especially by Goncharov, also by Francis Brown in some form.
So Hodge path is something in F0.
Yeah.
But in this case, F0 is trivial, isn't
Yeah,
it?
that's right. Yeah. So actually, right.
So in other words, there's no precomposition.
Sorry. So it means that actually the Hodge path, this path here, is actually uniquely determined. Right? That's what it means. Still, you still have these paths, and in fact, they're even better in a way. They're uniquely determined.
Just the identity, basically.
I don't know. I mean, the point is, yeah, I guess part of that means is that this path torsor has a preferred point, which you could call the identity. Yeah, sure. And then, okay, so then if I take this formal period and evaluate it on our period loop, we get what we would call an actual period. A highly transcendental p-adic number. So this means that zeta 3 is a p-adic period of a mixed state motive. And so the Kim function above is a polynomial in Coleman functions that are individually, in a certain sense, rationally defined, but with period coefficients that we kind of can identify and know and have come to love. And that's sort of what we would ideally hope for beyond the mixed state setting. And now, switching to the mixed state setting, there's work of David Corwin's with contributions from Owen Patnick and the same Martin seated over there. So suppose, right, so we're in our example again. So the example I started with, so Z is an open subscheme of spec Z, E is an elliptic scheme over Z, and X is the complement of the origin. We are assuming E does not have CM. Let's assume that here we have only one prime inverted, and let's assume that E has rank 1. Let alpha and beta be a kind of standard basis of the de Rham homology. So with alpha holomorphic and beta of type 2. And then, so then there exists a non-zero Kim function of this form. So we have our iterated integrals. And we have coefficients, so the coefficients are rather more abstract. They're just C1, C2, C4, C5. And now in a concrete example, so what this means that using our insight into the map from this global Selmer variety to the local Albanese variety, we're able to restrict the existence, we're able to establish the existence of a Kim function inside of quite a small vector space. But then if we want to really pin it down, then in an individual case with enough points, we can plug enough integral points, we can plug in those points, sort of cheat and solve for these coefficients. Right, but of course, one of our hopes is to gain more insight into these coefficients, and to be able to find them even in the case without enough integral points. Probably come very close to ending my talk. Maybe let me have a bunch of slides about how to connect what I said before with this. Obviously, I don't have time for that. I think I'll skip to the very end. Oh. And maybe I won't even do that. Let me just mention that, right, so we have this, our p-adic period point gives us a homomorphism from a subalgebra of the arithmetic unipotent fundamental group of the base 2 cubed. And it's reasonable to call image the space of unipotent p-adic periods or something, and to conjecture, I think it might be reasonable to conjecture its injectivity. But there's this, by the way, there's this competing recent work by Ancona and Fratilla. One thing that's a bit wrong about I think I want to finish by highlighting something wrong with our unipotent p-adic period, which is that it's unipotent. If you're used to working with mixed state motives have everybody seems to agree that, as far as I know, that the p-adic periods of the Tate motive are trivial. But it's not in general, people don't agree that p-adic periods, I think even in the relevant sense of the pure motive are always trivial. Whereas the thing we've constructed is sort of would have you think so. And so there's this other construction by these guys. They mostly focus on pure motives. That's sort of the place where they are able to get a not conjectural theory, but an actual theory. They do compare two. Okay, I think I don't have time to explain what they do. But in any case, they discuss the possibility of generalizing their construction. Their construction is heavily inspired by work of André. Sorry, not true. Sorry, of Yves André. A more recent mathematician. I'm sure they're also inspired by André in some way. Everybody's inspired by André in some way. But they're typically inspired more recently by and so they discuss briefly the possibility of extending their work to the conjectural category of mixed motives. One thing that is essential then is that whatever category of motives you work with has a special fiber over ZP, over FP, sorry. Anyway, but I checked carefully really that their construction, if you then specialize back to mixed state motives, it also gives you exactly the classical theory for mixed state motives. On the other hand, their construction doesn't sort of integrate Chabauty-Kim theory quite as cleanly as ours does. So one of the next things, I think, directions is to understand the relationship a little better. Okay, sorry, I finished exactly on time.
Questions?
There's some cute description of the tangent space of this like drawn analog of the local Fulmer scheme.
A description of the tangent space? I haven't thought about it. Yeah. And I'm gradually starting to get used to your question, but I don't think I'm gonna have anything interesting to say about it right now. I appreciate the question though. But why are you asking?
It's just me. I mean, this conjecturally finite type over cube scheme. Things I'd want to do with it, the tangent complex would be a starting point.
Sorry?
The things I would maybe want to do with it, the tangent space would be a starting point.
Okay, I mean, we might also want to do tangential localization, I guess.
Young man over there.
So the last equation you had for the elliptic curve case was actually fairly simple. Very nice. Have you managed